Hey guys, welcome back to Genius Learning. So in this video, I want to do an electromagnetism problem, and we're going to be using Gauss's law for electric fields to calculate the charge density and the Q enclosed, which is the charge of the sphere. So here we have a solid sphere that's radius A all the way to the outside, but we have a cavity in the inside which is of radius B, which is the orange part. So the orange part is hollow, right? There's a cavity, and then after the hollow part all the way to the edge of the surface is a solid sphere. And in this area there is a rho, which is charge density. And so they give us that the charge density, which is a function of R, because we're going radial, is equal to alpha R. Okay, so these are the things that are given in the beginning. And let's go ahead and find the electric field for three regions. We're going to find it for 0 to B, from B to A, and from A to a radial distance outside of the sphere. So we want to check the electric field in each of those areas. Okay, so the electric field for R less than B, okay, so that puts us in a region around here. So if, let's say we have a small r that goes to this length here, what would be the electric field there? Well, there's a cavity and there's charge density outside, so it's a solid sphere. And so the electric field inside the cavity is going to be 0, because the electric field inside an empty cavity is always 0. Okay, so that's one thing we need to always remember. All right, so now let's label that part A. Okay, so now part B is going to be the region between B and A. Sorry, that should be an A. Okay, so this is our new region here. So now let's use the Gauss's law formula for electric field. We have the closed integral of electric field dotted with differential area equal to Q enclosed over epsilon naught. And for any of you that have seen the previous videos where I derive this differential area for a sphere, and I give the example of electric field for Gauss's law, now we're going to use those differentials in this problem. So you'll see how we use all the integrals based on those videos and how we found the differential area and the differential volume. Okay, so I'm not going to go through it in this video, but I'm going to give a little sketch on it. So I'm going to draw a coordinate system here. Let's see, we got X, we got Y. And let's see, this is d theta, this is theta, right? We got a length out of R. This is a differential area on the sphere. Okay, and if we project it down to the XY plane, okay, remember that this was r sine theta, so that means this down here is r sine theta. We have phi going from the x to the y, d phi, another length in, and finally this arc length here is going to be r sine theta d phi. This arc length up here is going to be big R d theta. Okay. Okay, so I know I went fast through that part, but I have a whole video deriving this. And so I just did that to show that the differential area is on the left side, right? Because we want to know how much electric field goes through this surface. And so we need a flat surface in order to understand how much electric field is going through it. Okay, so the integral for the left side is going to be 0 to 2 pi, 0 to pi, and those two limits are from d theta and d phi. Okay, so differential area is going to be, we got the E, and then the differential area is going to be this arc length here and this arc length here, right? Because it's length times width. So this is the same thing as this, which is r sine phi, and then r theta is over here. So we got r squared sine theta d theta d phi, and all of that still equals q enclosed over epsilon naught on the right side. Okay, so if we evaluate this integral, we have no r to evaluate, and let's see, the sketch here I drew is with a capital R, but we don't have a fixed radius, meaning we have to check a radius of B and we have to check a radius of A, and we have to check the areas, you know, in between those two limits. And so we don't have a fixed R, and so for that case I can write this as a lowercase r. Okay, I could take the E out, and we already know what this is going to become from the previous video. So 4 pi r squared equals q enclosed over epsilon naught. All right, so from here, right, we need to figure out the charge enclosed. So now we need to remember that if we have density, all right, our Q is going to be a differential volume. So Q enclosed is going to equal rho dV, because we're in 3D in a sphere. Okay, so now the differential volume, right, is the same process as this, except we want an extra element here that comes out of the surface, right? So it's like a kind of like a cube. And again, if this is not clear to you, then just go back to the other videos where I derive it and I make it clear. And so then the differential volume, sorry, becomes 3 integrals. Okay, so I'm just gonna write everything out. I'm gonna write Q enclosed, and the rho is alpha r. So let's write the 3 integrals first. Okay, I'm gonna write alpha r, that's the rho, and then here is gonna be r squared sine theta, just like it was here, except now we have dr d theta d phi. So here the limits of integration, since we're interested in the region between A and B, then we're going to do final minus initial. So we start at B and we go out some distance r, right? That's before the A, and we check the electric field in this area. So that's what this integral is covering. And theta goes from 0 to pi, phi goes from 0 to 2 pi. So again, these limits of integration and everything that I'm doing with these integrals, I have in a previous video. So let's evaluate this and let's see what we get. Okay, so this Q enclosed is still just this piece right here. All right, so Q enclosed is going to equal, we could pull out the alpha. Okay, we're going to get a 2 pi from the d phi, and we're going to get a 2 from the integral of sine d theta with the limits of 0 to pi. Okay, and then the rest of the integral is going to be the dr. And so we're going to get r to the 4th over 4 minus b to the 4th over 4. Okay, so this r to the 2nd combined with this r to make r to the 3rd. And then once we take the integral of dr, we add 1 to the top, so that'll be 4. And then we divide by 4. And here I just put in the limits already, so I evaluated it. So this q here is good to go. We can simplify it further. And so if we do that, let's take a look. I'm gonna write this starting up here now. And I'm gonna include the electric field again. So on the left side is the electric field, 4 pi r squared. Okay, and on the right side, now we have this entire expression here, but if we take out this 4, that'll cancel out with this 2 and this 2, which make another 4. So we can simplify that. All right, and what we're going to be left with is alpha pi, and we got r to the 4th minus b to the 4th. Everything is still over epsilon naught. Okay, so that's it. Now let's combine everything and the electric field. So we're gonna pass all this to this side, but this pi's are gonna cancel, and we're gonna be left with alpha r to the 4th minus b to the 4th over 4r squared epsilon naught. Okay, so this is the electric field. I put a vector there, it's in the radial direction going outward. And this is for the electric field for the region between B and A. Okay, so now let's find the electric field for the last part, C, which is going to be the radius greater than A. So some region out here that is greater than A. So this is what we're interested in. Okay, so starting off with Gauss's law for electric field equation. Okay, Q enclosed over epsilon naught. Okay, starting off with this. Now, I'm not going to derive the left side again, right? Because it's going to be the same exact thing. So I'm just going to write E 4 pi r squared, right? Which is what we got here. And on the right side, we're going to do Q enclosed over epsilon naught. All right, so we need to find what Q enclosed is. So let's solve it out by itself. So Q enclosed is equal to the charge density and differential volume. So it's dq rho dv. But when I integrate this side, the differential and the integration cancel out. So I'm not going to write dq here, but that's what it is. And rho dv. This side here has 3 integrals, right? So let's write those out. Q enclosed, we got 1, 2, 3, rho, right? And then we have r squared sine theta, dr d theta d phi. Okay, so our limits of integration for phi are going to be from 0 to 2 pi. for theta is 0 to pi, and for the r, with the differential radius, we want the area outside of the sphere. Okay, so we're gonna write here B to A, because that's the only area where charge is enclosed. Okay, so from here to here is the only place where we have charge density enclosed in order for us to include it in our differential volume element measuring our charge. Okay, so basically there's only charge in this green region, and even if we want to check the electric field outside, we only express the charge enclosed for this part here. Okay, so we know what rho is, so let's put alpha r squared sine theta dr d theta d phi. So I just changed the rho. Okay, so all three integrals, 0 to 2 pi, 0 to pi, and b to a, equals q enclosed. All right, so let's evaluate and let's see what we get. For the phi, we're going to get 2 pi. For 0 to pi, integral of sine, we already know it's going to be the same thing, 2. We can take the alpha out, and so now the only thing we have left is the integral from b to a of r to the third dr. Okay, so I didn't show this step last time here, but this is what it looks like before you integrate it, making it a 4 over 4. So it's going to be the same thing on this side. Okay, so q enclosed is equal to, combine these two, 4 pi alpha. The integral of this is going to be r fourth over 4, and I'm going to put in the limits of integration already. So that's going to be a to the 4th over 4 minus b to the 4th over 4. All right, and if we take out this 4, it'll cancel with this 4, leaving us with q enclosed of pi alpha a to the 4th minus b to the 4th. Okay, so now let's plug this into our electric field equation, and we get here electric field of 4 pi r squared. I left it on the left side for a second. Well, what did we get for q enclosed? This expression here, right? Alpha a to the 4th minus b to the 4th over epsilon naught. And if we move all this stuff to this side, we have the pi's that cancel, and the electric field is now alpha a to the 4th minus b to the 4th over 4 epsilon naught r squared, and that's all in the radial direction. All right, so this is the electric field that exists outside. Okay, so this is outside or greater than a, and you would think that outside of this sphere there would be no electric field, since we have the charge enclosed only in this region here. But if we take a look at what we have here, R goes like 1 over R, right? So what that means is that the electric field is proportional. So I should say proportional to 1 over R, or R squared. Okay, so as I get farther and farther away, right, increasing here, then I will be decreasing my electric field. So that makes sense, because since we're outside now of the solid sphere that has charge in it, the farther we go away, the less the effects of the electric field that we're gonna feel from the edge of this sphere. Okay, and so then we could see that here. Electric field is proportional to 1 over r squared. And that's it. All right, so for practice or for understanding better in these types of problems, I would suggest understanding differential area and the differential volume that comes from the charge enclosed. Because when you look at this sphere and it's mixed up with a bunch of layers, you have a cavity in the inside, and then you have some charge density in this medium here, and then, you know, on the outside you want to check if there's electric field. Understanding each part or each volume element that you're trying to acquire helps you understand to do the math and the integrals. The integrals are where the biggest mistakes happen. So these limits here, right, are better understood when you understand what's going on with the volume elements, okay?